All right, guys. So this hopefully is going to be our last video as we prepare for the, chemistry SOL. Um, this we're just going over that new practice SOL that I made for you guys in Schoology called the 2026 practice SOL. Remember, this is designed based on the number and types of questions you'll see on the new version of the SOL that is starting on 2026. And right now we're kind of into the section which is kind of the end of the year stuff. And the main focus is kinetic molecular theory, like states of matter, that kind of thing, gas laws, and energy heat calculations, and some kind of just basic definitions of the study of thermodynamics. So um, it's a lot of stuff, but it's not going to be too complicated. So it's mainly just focus on the concepts, focus on the definitions, focus on the vocabulary, because a lot of the stuff in this part of the unit, we use different words interchangeably and they mean the same thing. Like the term enthalpy and heat are the same thing. The symbol H isn't heat, the symbol H is enthalpy, but since enthalpy and heat are the same thing, then that means that when you see H, you can think heat. When you see the word enthalpy, you can replace it with the word heat. These are all energy. So, if you need to, you can replace it with a unit of energy. So instead of heat, you can say joules or kilojoules or calories, right? Instead of enthalpy, again, joules, kilojoules, calories. Okay. Um, and so it's just getting used to those definitions. And when it comes to the calculations you have to do, it's really, if you look at the units and you understand how dimensional analysis works, you can do most of the calculations just fine. It's just getting over the fact that you're going to see some foreign terms to you that, that we're going to throw out to you in class, but you might not see them that much and you might not be used to them. And so get used to them for yourself because you have to take the SOL on the 20th, right? Understand enthalpy is H. Change in enthalpy is triangle H, delta H. Delta means change in. So delta T is change in temperature. Delta H is change in enthalpy, which you can think of as change in heat, right? Change in energy. Okay. Um, all right. So anyway, let's just get back to it. And when we come across those questions, I'll probably repeat myself, but all right. So we left off, we just did question 34, which was review of phase diagrams. So hopefully we got that. Remember, solid, liquid, gas, triple point, critical temperature. Normal means 1 atmosphere or equivalent. So 760 millimeters of mercury would be the same place right here, right? This line is melting, freezing. This line is vaporizing. But if you cross this line down here, that's sublimation and deposition, right? Okay. So all that good stuff. All right. So now we're on to question 35. Okay. And this one's just kind of a vague question. It's probably going to be more detailed if they ask about this, but like remember we have the ideal gas law that's PV equals nRT. Okay. Um, right? And if we go to, one of your cheat sheets, um, you know, that's the ideal gas law, right? And then you have the combined gas law, a little reminder that whenever you're using gas laws, temperature needs to be in Kelvin. How do you convert Celsius to Kelvin? You add 273. So just this is a good thing to write down all in kind of one location on your memory dump formula sheet that you're going to create. Um, don't worry about the R values. I've never seen so there might be an ideal gas law question on this year's test. On previous SOLs, on the questions that they've released, I've only seen one question where they actually used the ideal gas law, and on that one time the ideal gas law showed up on the SOL, they gave you the R value in the question. So if they give you an R value, hey, you use the ideal gas law. But if they're not going to have you memorize all these values. You do have to memorize Avogadro's number, right? Unfortunately, you don't get a formula sheet. So the stuff on the suggested cheat sheet is the stuff I suggest on your memory dump. You're going to have to calculate percent error. You're going to have to calculate percent yield. You're going to have to calculate molarity. You're going to have to calculate mass number, right? You're going to have to do all this stuff, right? But you don't get the stuff on the back of your periodic table that you're used to. You don't get the formulas. You need to know the concepts, right? You don't get the pH and the POH equation and that they add up to 14. You have to know it. You have to know that this is hydronium and, you know, this is hydroxide, and hydronium and H plus are the same thing, right? This represents the molarity of H plus or hydronium. This represents the molarity of hydroxide, right? So sorry, I'm making this long-winded because it's stuff that you know, as you're preparing for the SOL, you know, make sure you get that memory dump cheat sheet ready. Make your own, write it down, have it memorized, try to recreate it, practice it, take 10 minutes and try to recreate it from memory, and get ready for that and get in that mindset and go do it when you take the SOL. And I guarantee it's good for 3 to 5 questions that you would have gotten wrong because you forgot the concept. But if you have it written down and you can reference it, you're going to be in good shape. All right. So for an ideal gas, we ignore particle volume, right? We don't care about helium being smaller than neon. It doesn't matter because the particles are so spaced out that the actual size of the particles are taken up is so much smaller than the space between them that we ignore the particles themselves. So an ideal gas, we don't care about the size of the particles, right? We would care about, if we're comparing liquids and their densities, it really is going to depend on, well, how big is each particle, right? But for gases, we don't care about how, you know, big or small the individual particles are. We ignore them. And the other thing we ignore is when particles bump into each other, especially like polar particles. If this side's positive and this side's negative, when they collide, they're going to attract. Or if this side's negative and the other side's positive, they would repel, or if they're both negative, they're going to repel each other. If they're both positive, they're going to repel each other. But we say in the gas state, when they bump into each other, nothing happens. They don't stick together. They don't repel each other. We call it an elastic collision. Energy is conserved throughout the collision. So their collisions are elastic. How should we interpret that in chemistry? It means no intermolecular forces. Okay. So a gas behaves ideally when the collisions, when they don't stick together, when they collide, and when they're really far apart. So that's high temperature, because when they move really fast, they won't stick together when they collide. And low pressure. Low pressure means they're really spread out. And while the more spread out they are, the more we can ignore the size of the particles, right? When these two things are far apart, the size of the particles aren't taking up much space compared to the space between them. But when they're close together, obviously the size of the particles matters. So high pressure is not ideal. When they're close together, you can't ignore particle size. Low pressure, ideal, right? If they're moving really slow and they bump into each other, they might stick together and condense, right? But if they're moving really fast, they might just bounce off each other, right? So moving fast, high temperatures, that's ideal. Really far apart, you can ignore particle volume, that's ideal. That's what ideal behavior kind of means. Okay, so if we go back to the question, what assumptions about matter in the gas state do we make to make a gas behave ideally? It means we ignore particle volume, so the size of the particles is negligible, and it means the collisions are elastic. All right, those are the two assumptions. All right. All right, on to number 36. All right, so here we have a delta H. Remember, that means change in enthalpy. Now, when it gets a specific subscript, that means for vaporization. So what is this telling me? It's telling us the heat, which is also called enthalpy, the molar heat of vaporization, or you could call it the enthalpy of vaporization. It means the same exact thing. For water is this. What is that telling you? It's telling you it takes 41 kilojoules of energy to vaporize 1 mole of water. That's what that measurement means for water. 41 kilojoules to vaporize 1 mole. Okay. Now here we have the same measurement, the molar heat of vaporization for another compound, and notice it's a lot lower. It only takes 12 kilojoules of energy to vaporize 1 mole of this, where it takes 41 kilojoules of energy to vaporize 1 mole of this. Okay. What accounts for the difference? Remember, vaporizing things is making particles break apart. You're not breaking the bonds within the molecule. I'm not like, you know, pulling an oxygen off of a water molecule. I have 2 water molecules that are connected with each other via hydrogen bonding, right? IMFs. And what does vaporize mean? It means I make them move fast enough, right? I increase the temperature fast enough that they're moving fast enough that they break free from each other. So what's being broken? IMFs. So the stronger the IMFs, the more energy required to vaporize. So why does water have such a stronger molar heat of vaporization compared to CF4? It has stronger IMFs. All right, so that's what we're looking for. Water has polar bonds. It's true, but carbon tetrafluoride also has polar bonds. So that has polar bonds, that has polar bonds. Remember, this one is polar, this one's not, right? This is symmetrical. So this molecule is nonpolar. Its only IMFs are London dispersion forces. This molecule is polar. It has hydrogen bonding and London dispersion forces. So, it is because water has polar bonds, but it's not the polar bonds that cause the IMFs. It's the fact that it's a polar molecule. So you want to forget it. You want to watch out for that. The hydrogen bonding between water molecules is weaker. No, we just said it was stronger. Carbon tetrafluoride has stronger IMFs. No, if it had stronger IMFs, it would take more energy to vaporize it than water. So water has stronger intermolecular forces compared to carbon tetrafluoride. That's the correct answer. Okay. So let's just go back to my key and see if we have any notes for this one. All right. So again, if you have access to my notes in Schoology, so if I don't say everything on here, you might want to pull it up and go. But like this is the stuff I was just talking about for ideal conditions. What makes it ideal? Okay. All right. So here, right. So molar heat of vaporization is the amount of energy. In this case, it was kilojoules. It doesn't have to be kilojoules. It could be something else. It could be energy per mole. That's usually what delta H's are, energy per mole, but it could be energy per gram, right? That doesn't matter. It's just, so if it's energy per mole, if I multiply by moles, that'll give me energy. If it's energy per gram, if I multiply by grams, that'll give me energy, right? Okay, so that's not a big deal. So what we're saying is for water to do this, for 1 mole of water to do this, it takes that much energy. For 1 mole of carbon tetrafluoride to do it, it takes that much energy. Remember, to vaporize, to melt things, you're breaking IMF. So you're not breaking bonds, you're breaking intermolecular forces between the molecules. And you could use the word bond if that IMF is a hydrogen bond, because you are breaking hydrogen bonds between water molecules. But remember, you're not breaking the hydrogen-oxygen polar covalent bond that's between the atoms within the molecule, just the forces that are between the molecules, okay? All right, so let's go to, periodic table. Where am I going? I'm going to Schoology, back to Schoology. Here we go. All right. So we go to number 37. All right, so we have a potential energy diagram, okay? Sometimes they're called reaction coordination diagrams, okay? Sometimes they're called, potential energy diagrams, maybe reaction coordination diagram. This isn't time right here on the x-axis. It's the stages of the reaction. So you have the beginning stage, the middle stage, and the end stage. What do we call the beginning stage? The reactants. So right here, this is the energy or enthalpy or heat, kilojoules, of the reactants. This is the energy of the products. This is the energy of the in-between. We call the in-between, sometimes it's called the transition state, sometimes it's called the activated complex, okay? Now, all you need to know is the difference between final minus initial is the delta H. It's the change in energy of the reaction. So if I can read this 2 different ways. I can read it from left to right. And if I'm talking left to right, I'm talking about the forward reaction here. So this represents A and plus BC, which are the reactants. And then over here would represent AC plus B. All right. And then what's here? The jumbled up mess of everything before they kind of get a little bit more stable and turn into their products, right? But I could also read this chart from right to left. If this is a reversible process, then if I read it from right to left, then these are the reactants, A, C, and B, reactants on this side, products on this side. So going this way, the reaction increases in energy. It goes from 50 to 100. But going this way, it decreases in energy, going from 100 to 50. So the forward reaction is absorbing energy. It absorbs 50 kilojoules. The reverse reaction releases the same amount of energy, but it's releasing 50 kilojoules. Okay. So if they're talking about the forward reaction is endothermic because it's absorbing energy. If they talk about the reverse reaction is exothermic because it's releasing energy. Okay. Remember, the forward reaction, reactants to products. So here's the initial, here's the final. Remember, delta is final minus initial, so 100 minus 50. But if we're talking about the reverse reaction, we would do 50 minus 100, and it would be negative 50. Okay. All right. So the enthalpy change for the forward reaction we just said was 50 kilojoules, and it was positive 50. Okay. 100 for the products, 50 for the reactants. Final minus initial is how you get your delta. So products minus reactants, right? The final part of a reaction is the products. The initial part of the reaction is the reactants. So products minus reactants gives you your delta H. Okay. But just remember, if you're talking about the forward reaction, this is the products, this is the reactants. If this said the reverse reaction, that would be the products and that would be the reactants, and it would be 50 minus 100. Okay. So the reaction is endothermic because it's absorbing energy, right? Overall, we went from 50 to 100, so that's an overall absorption of energy. The activation energy for the reaction. So activation energy is top of the hill to the reactants. So for the forward reaction, 50 to 250, so 250 minus 50 is 200. So the activation energy for the forward reaction is 200. For the reverse reaction, remember, delta H is the same value for the forward and the reverse reaction. It's just, is it endothermic or is it exothermic? So going this way, absorbing that much energy, going that way, releasing that much energy, right? Okay. And then if the reverse reaction had a catalyst, the activation energy for the catalyzed reaction would be less than what? So basically it's asking what is the activation energy of the reverse reaction. So remember, the reverse reaction, these are the reactants. So the top of the hill to the reactants would be 250 minus 100. So 150 is the activation energy of the reverse reaction. But if you add a catalyst, remember what a catalyst does is lowers the activation energy. So it'd be lower than 150. All right. So hopefully that makes sense to you. Let's see if we had any notes going over anything like that. Right. And just get used to it. If you see it this way, you know the forward is endo, the reverse is exo. There's your delta H. Is just, should you report positive or negative? It depends on, was it absorbed or released, right? And then top of the hill to reactants, top of the hill to reactants. That's how you get your activation energy. Okay. Let's go to the next one. All right. So student wants to speed up a chemical reaction. All right. How can they do it? All right. So remember, you want more collisions. If you can get more collisions, you're going to get a faster reaction. So how do you get more collisions? More particles. You get higher concentrations of stuff, right? Remember, when we used the 6 molar HCl, when we reacted with the zinc, it started bubbling really, really, really fast, right? That's because it was 6 molar. If I used 0.01 molar concentration, it wouldn't go that fast, right? So like, if you have a solid, crush it up, break it up, right? How do you get salt dissolved faster? How do you get sugar to dissolve faster? You break it up, right? You speed it up, you increase the temperature, you make the particles move faster. If they're moving faster, they're going to collide more, right? If you want to speed up a reaction, it's about getting more collisions, right? And more collisions with greater energy is what you're hoping for, because the particles don't have to just collide, they have to make it over the hump, right? They have to have enough energy, and we call that the activation energy, right? So another way we could get more collisions to get over the hump is lower the bar. We could lower the activation energy, so add a catalyst. So the different things we can usually do to increase the rate of reaction, which means make the particles collide more, is add more reactants, right? Just have higher concentrations of reactants. If you have a solid, crush it up, break it up, cut it into strips, right? We're increasing surface area, right? Greater surface area means more places for collisions to occur, so you get more total collisions. More total collisions equals reaction happens faster, right? A and B can't form AB until A and B collide, right? So you got to get collisions, but not every collision results in a reaction. So But if we can increase the number of collisions over a given amount of time, we should have a faster reaction, right? So it's about increasing the reaction. So what else can we do? If we have gases, we can decrease the volume and force them closer together. If they're closer together, they're going to collide more often, right? We could heat them up, make them move faster, but if they're still in the same amount of space, if they're moving faster, they're going to collide more often. It's kind of like, how do you increase the pressure, right? Right? If you want to increase the pressure, you're trying to get more collisions. If you want to increase the rate of reaction, you're trying to get more collisions. That's essentially what we're trying to do here. So if we go back to the test, right, adding more product's not going to do anything, so don't click that one. Yeah, cut the magnesium up into pieces. That increases the surface area, right? So that'll be more collisions. Don't use a brick, right? Use cut up pieces, right? Use a magnesium strip, not a big brick of magnesium, right? Nope, that's not going to do anything. Add a catalyst. That always speeds up a reaction. Increase the concentration of this reactant. Yes. Increase the temperature. Make the particles move faster. Yes. Now remember, it said 4, so we've identified the 4. Now this one's kind of an odd man, right? A lot of people might think this one because it says HCl with a pH of 5 instead of a pH of 1. Remember, the lower the pH, the higher the concentration of HCl. So it's the pH of 1 has a higher concentration. So pH of 5 would be more dilute HCl. Right? You want to increase the concentration to have more collisions, not decrease it. So don't fall for that little trick there. All right. All right. So here's just kind of our definition. Remember, enthalpy. The symbol for enthalpy is H. Okay. It's so technically H doesn't mean heat, but you can think it means heat, but technically enthalpy is H. Okay. What is another word for enthalpy? Heat. All right, great. All right. What is the symbol for enthalpy change? Remember, if you put a triangle in front of it, it's called delta. In front of it, it means change in that. So if enthalpy is H, delta H is change in enthalpy. Okay. Remember, enthalpy is an energy value. Remember, a negative energy value means energy released, exothermic. All right. So I should probably say, what does a negative energy value? It means what I'm probably looking for is energy is released, right? Released to the surroundings. So remember, you're part of the surroundings. So if a reaction that's exothermic is happening near you, it's releasing heat to you, you feel hot. But the reaction is losing heat. Where's that heat going? It's going to you. You're feeling hot. You're part of the surroundings, right? And that would be an exothermic reaction. Reactions with a negative delta H tend to be favored over reactions that have a positive. So what does that mean? It means exothermic is favored in terms of endothermic, but that's only if you're just looking at enthalpy. What we want to understand is whether a reaction is favored or not doesn't just depend on enthalpy change. It depends on something else, which we're about to talk about here in a second. So, but in terms of just what is favored in nature, according to thermodynamics and enthalpy change, when something is favorable and it has a negative delta H, the reason it's favorable is because the delta H is negative. So for delta H, negative delta H more likely to occur than positive delta H. It doesn't mean endothermic can't happen. We know ice melts when we take it out of the refrigerator, right, or out of the freezer. So we know that endothermic process happens spontaneously. It's favored, but right, in general, exothermic favored over endothermic. Okay, so when it comes to enthalpy change, negative good, positive, bad, I guess, but it's not that it's bad. It's just enthalpy change. Right, the universe is losing heat, so anything that releases more heat usually favored. Okay, all right. So the other thing, entropy. Entropy gets the symbol S. All right. So if you see delta S, that means change in entropy. So entropy is S, enthalpy is H. H and enthalpy is the same thing as heat. You can think of it as heat, but okay, so whatever. All right. Anyway, sorry. All right. Now, what is entropy? It's randomness or disorder. It's how chaotic, how disordered are the particles, right? And so you should understand gas particles are moving all around and they're all over the place. they're very disordered. Gases have high entropy. Solids have very low entropy. They're very ordered because those particles are kind of stuck where they are. They just vibrate, right? So solids have low entropy, liquids kind of in the middle. Gases have very high entropy. Liquids are more disordered than solids, okay? But the difference between solid and liquid in terms of how random they are is small compared to the difference between liquid and gas. Gas is very disordered, very random, okay? So what does a positive delta S mean? A positive delta S means the products are more disordered than the reactants. As the reaction proceeded, it increased in randomness, it increased in chaos, it increased in disorder. Remember, delta is products minus reactants. So if you have an increase in randomness, that means the products are more random than the reactants, okay? Or more disordered, more chaotic. Okay, that's the way to think about entropy. For entropy, it's a positive entropy that's favored. So that's kind of the balancing act in thermodynamics. When you have most reactions that are endothermic also have a positive delta S. So I'm not favored in terms of enthalpy change because it's positive, but I am in favored in terms of entropy change, delta S, because delta S is positive, okay? And then the opposite is true for exothermic. Most exothermic processes also decrease in randomness. They have a negative delta S. So reactions that are exothermic, they're favored because the delta H is negative. They're not favored in terms of entropy change because the delta S is also negative. Now, anytime you have a reaction that has a negative delta H and a positive delta S, that's always favored, okay? But most things are reversible, which means most things are sometimes favored going this way, other times favored going this way. What's usually the main deciding factor? It's temperature, right? Why does the ice melt when I take it out of the freezer? Because even though it's an endothermic process, and endothermic processes aren't favored in terms of enthalpy change, because the temperature's too hot, right? Why does this combustion reaction happen why does this reaction happen even though it's decreasing in entropy, and that's not favored in terms of entropy change? Well, it must be very exothermic. It must be releasing a lot of enthalpy, right? That kind of thing. All right. So just kind of lock down those definitions, right? Don't get hung up when you see the term entropy on the SOL. Just symbol S, delta S positive, good, delta S negative, bad. What does S mean? Randomness, disorder, chaos, right? Positive delta S means more disordered. A negative delta S means your products are more ordered than your reactants, right? If you show a gas subliming, deposing, that would be a negative delta S, because you would have gas particles going to solid particles and the particles are becoming more ordered. So that would be a decrease in entropy, okay? All right, so now we go to 41. As soon as I see this diagram, I know that the dotted line's the catalyst, right? Because what does the catalyst do? It doesn't change the starting point and the stopping point of the reaction. It changes the middle part. It changes the energy barrier between the reactants and the products, right? So that difference, right? Remember, from here to there is the activation energy. What does the catalyst do? It lowers the activation energy. So path 2 is a catalyst path. Path 1 is the uncatalyzed path. The delta H is 50. It's positive 50 if we're talking about the forward reaction. It's negative 50 if we're talking about the reverse reaction. So all those things I can get a glance at just by looking at this diagram. So if this is the diagram of this reaction, we know the forward reaction is endothermic, positive delta H, and the reverse reaction is exothermic, negative delta H. Okay, which of the following most likely accounts for the difference between reaction path 1 and reaction path 2? Remember, we just said path 2 is the catalyst, path 1 is not catalyzed. So the presence of a catalyst in path 2. There we go. Now, if they asked us for the delta H, it would be positive 50. If they talked about the reverse reaction, it would be negative 50, right? They talked about the activation energy. For the forward reaction, it would be 150. Okay. For the reverse reaction, it would be just 100 because the difference is 50, right? Okay. All right. So the next one. So what do you got to remember about the gas laws? It's really just the relationships, right? So pressure and volume, inverse relationship, right? If they have a negative sloping curve, but it's a straight line, don't pick that one. Inverse is curved, okay? But direct, which pressure and temperature have a direct relationship, that's going to be a constant slope. Volume and temperature have a direct relationship, that's going to be a constant slope. And volume and moles have a direct relationship, that's going to be a constant slope. So those are our answers for the relationships there. Okay. Let's go back to my notes. We just did that one and we just did the entropy one. You might want to go and check these out because I can spend a lot of time going over those on the video. All right. All right. So remember, if you have, anytime you do initial times initial equals final times final, that's always inverse. If you have initial over initial equals final over final, that's always direct, right? So you don't need to know it's Boyle's law, but that's Boyle's law, Gay-Lussac's law, Charles' law, right? You need to know what the equation is and you need to know to plug it in, but you don't need to know the name. You need to know what the relationship is. And remember, if you're plugging in temperatures, Kelvin, don't put in Celsius into these equations, okay? All right, whoops. All right, so we're going back. All right. All right, so here, the volume of a balloon is filled with CO2 gas at 5 liters and 50 degrees Celsius. What will the new volume be if the temperature is increased to 100 degrees Celsius? All right, so, sorry, that might be the answer. It might not be. I haven't looked at it yet. But anyway, so remember, don't guess 10. A lot of people are going to guess 10 because they're going to be lazy. They're not going to do the math because they saw that the temperature went from 50 to 100, and that's doubling. And so if you remember that volume and temperature have a direct relationship, if the temperature doubled, the volume would double. And that's true, but only if it doubled on the Kelvin scale, right? Doubling on the Celsius scale doesn't mean it doubled on the Kelvin scale. If it doubled on the Kelvin scale, then yeah, it would go from 5 to 10. It would double. But it didn't double. It just increased. So it's going to be greater than 5. So we can eliminate this answer, right? That can't be the correct answer. And we can eliminate this one if we understand that it didn't double on the Kelvin scale. So it's going to be this one or this one. So by process of elimination, the volume has to get bigger. So it's going to be this one. All right. So that's going to be the answer. But let's see if we have it worked out. Right. Right. So process of elimination, if we really understand, KMT and gas laws, like we got it, right? But if we wanted to do it, we're doing V1 over T1 equals V2 over T2. We're solving for V2. V1 was 5 liters. T1 was 323 Kelvin. V2 is what we're solving for. And T2 was 373 Kelvin. So all we're going to do is 5 times 373 divided by 323, and that'll give us our volume. So it comes out to be 5.77, which is our answer choice. Okay. All right. So here we have a heating curve, right? But it's technically a cooling curve because we're cooling it down, right? Right. Temperature's decreasing, then it stays the same, then temperature's decreasing, temperature stays the same, temperature's decreasing. So how does it go? A to B is just a gas, right? C to D is just a liquid. E to F is just a solid. B to C would be condensation. D to E would be freezing, right? But if I'm anywhere here, I'm just a liquid. If I'm anywhere here, I'm just a gas. If I'm on this line, I have some solid and some liquid. If I'm on this line, I have some gas and some liquid, right? So remember, if you actually have temperatures here, right, this would be the boiling point / point of condensation, and then this temperature would be the melting point / freezing point, right? So to calculate energy change, C to D or D to C, C to D, D to C, remember, if the temperature is changing, we need specific heat capacity. And what equation would we use? Q equals MCAT, right? Q equals MCAT. So what about B to C or C to B? Remember, that's vaporization or condensation. So we would need the delta H, the molar heat of vaporization. Okay. And then D to E or E to D, that would be melting or freezing. That's what the molar heat of fusion is for. So this is for vaporizing or condensing. This is for melting or freezing. Okay. All right. Last question. Okay. So they gave us the heat of fusion for water. Remember, this is the energy for for melting, freezing. They also gave us the heat of vaporization for water. This is the energy for vaporizing or condensing. It's positive if we're vaporizing because that requires energy. It's negative if it's condensing because it releases that same amount of energy. Okay. So positive if we're talking this, we're use positive this number if we're talking about melting, negative that number if we're talking about freezing. So as soon as I see they're talking about condensation, I know I'm not using this value. This value has no use to me, right? It's only the heat of fusion. Now, let the units tell you what to do, right? You have grams of water. You're given this measurement that says energy per mole, and notice you just want energy. So if you have energy over moles and you want just energy, what do you multiply? You multiply by moles. If I take this value and I multiply it by moles, moles will cancel out and it will just give me kilojoules. So what do I have to do? I got to convert 25 grams of water to moles. And then once I have moles of water, multiply it by this, and that will give me energy. Okay. So here's how the dimensional analysis works. All right. So again, don't use the heat of fusion. Now, if this said freezes, then that's when we're using the heat of fusion and we're not using this. If it said melt, we're using this value. If it says vaporize or condense, we're using this value. All right. So what do? We take our 25 grams of water, we divide it by the molar mass of water. That gives us moles of water. Then what do? We multiply by this thing. How is it a conversion factor? We put the 40.7 kilojoules on top. For every 1 mole of water on the bottom, that'll cancel out moles of water and give you energy. So it'll take around 56.5 kilojoules. If they said the same thing, but it said freeze here, then what's going to change? Instead of 40.7 here, we're going to plug in 6.5 right there. And then we'll do our math. Okay. All right. So again, make sure if you haven't yet, you go in to, sorry, it was this one. Okay. So you go in to our Schoology prep course and you go to the TestNav link and you take the chemistry practice SOL here. Now, remember, if you've already watched the video of me going over those problems, that's fine. You don't have to do it, but you need to be familiar. What do you get? You get this calculator, Desmos. Know how to use it. What else do you get? You get this periodic table. It's not going to be on paper. You have to click on that and then unclick it to get out of it. And then once you're in it, you got to click one of these guys, one of the elements for all the information to be popped up here. All right. Okay. You don't get any formulas. If there's an ideal gas law question, I guarantee you they'll give you the R value. If they don't, that is a brand new level of difficulty that they're adding to the SOL that we are not anticipating. But you get the R values if you take the AP Chem exam. So like the fact that they wouldn't give you an R value is pretty dumb in my opinion. So, expect the R value. But what will you not get? You're not going to get any of this stuff. The stuff that's on, the stuff that's on my suggested cheat sheet, right? There's a lot of stuff on here. You don't have to have it all. You probably know a lot of it already and you don't need reminders, right? But here, those energy calculations that we were just talking about, here's kind of some cheat sheet for you, okay? Right? So you need to make your own. They are going to talk about polyatomics, but whenever they bring up polyatomics, these are the most important ones. These are the ones that they expect you to know. If they bring up something like maybe permanganate, they'd probably give it to you in a chart and you'd have to know what it means, right? MnO4 with a 1- charge, and what would you do with it? Okay. But they're not going to give you the gas laws. They might give you the ideal gas law, probably not. But if they give you an R value, you got the ideal gas law. You need to know this one. Remember, if temperature is constant, cover it up, and that's the gas law. That's the equation you use. Just remember always be in Kelvin, right? You will have to calculate pH. You will have to maybe calculate pOH to then calculate the pH somehow, right? That'll be on there. Molarity will definitely be on there. I would write down a mole map. If you don't know how to go from grams to moles or moles to grams or grams or moles to particles or particles to moles or volume of a gas at STP, I would write a mole map too, right? But definitely molarity, right? Definitely percent error, probably 2 questions with percent error, probably 1 question with percent yield, right? Okay. Right? You can add more to this stuff. Right? Take the back of your periodic table with all the formulas on it. The stuff that you like to look up there, add it to your cheat sheet and do the memory dump technique. Again, that'll be good for at least +3 questions better than what you would do if you don't do it. I guarantee it. All right. So if you do it and you were gonna get a 0 on the SOL, hey, you'll get a 3, or something. But do it. It's untimed. That means you can take 15 minutes before you read question 1 and do a memory dump. And then once you have the memory dump and you've used all your scrap paper, you can raise your hand and you can ask for more paper. And then if you run out of paper, because you are going to want to write down some work for some of the questions. Not all the questions. A lot of them you can do in your head, but some of them you're going to want to write down. All right. Like a grams to grams stoich question. Probably want to write that one down. If you run out of room on your scrap paper, you raise your hand. Your proctor walks over. Right? It might take 2 minutes, right? There's a big room. There's a lot of people raising their hand. There's only so many proctors. Just keep your hand raised, right? Don't rush. It's not time. When they get to you, ask for another sheet of paper, write it down, and then continue working. Take your time. All right. All right. Anyway, that's longer than I wanted this video to be, but hey, it's it, right? You got it. Do your best. That's all we can ask for. All right. Good luck.